Imagine holding the world in your hand. Your smartphone, your laptop, your car. Everything you touch today relies on one tiny, almost invisible piece of technology, the microchip. These small wonders are behind nearly every device that keeps our world moving, from the moment you wake up to the moment you fall asleep. It's incredible to think that something so small can have such a huge impact. But have you ever wondered how these microchips come to life? What exactly happens inside the factory where they're made? How do raw materials get transformed into these powerful little processors that control everything from a car's engine to the device in your pocket? These tiny machines are the brains behind modern technology. Have you thought about how something so small can control devices that are so complex? What makes them so powerful? How are they made? Let's step inside the factory and uncover the secrets behind microchips and see how they're created. But before we start, kindly subscribe to this channel and turn on notifications. Also, like this video and share so many people can see it and learn. To truly understand how microchips are made, let's take a step back in time. The first microchip was created in 1958 by 𝗕𝗂𝗶𝗵𝗵 at Texas Instruments. His invention, the integrated circuit, changed everything. It made it possible to shrink down the size of electronic components, laying the groundwork for the compact devices we rely on today. Since then, microchips have evolved at an incredible pace. In the 1970s, companies like Intel started mass-producing microprocessors, the small but powerful brains behind computers. Today, microchips are everywhere. They power our smartphones, home appliances, vehicles, and even make space exploration possible. As technology has advanced, so has the process of making microchips. It now requires high-tech machines and an immense amount of skill. The chips of today are smaller, faster, and more powerful than ever. Some of them are so tiny that they can pack billions of transistors into just a few square millimeters. So, how does this process happen? What steps turn raw materials into these high-tech marvels that run the world? Let's take a closer look at how these tiny but mighty chips are created. You won't believe how it all comes together. It all starts with one crucial material, silicon. Silicon is one of the most abundant elements on Earth, and it's perfect for making microchips because it works well as a semiconductor. This means it can conduct electricity, but not as well as metals like copper. That's exactly what's needed to control the flow of electrical signals in a microchip. The process begins with silicon wafers. These are thin, flat discs made from purified silicon. To get these wafers, a large cylindrical block of silicon called a boule is grown. This is done through a process known as the 𝗕𝗂𝗀𝗃𝗃 method, where silicon is heated to high temperatures and carefully pulled into a cylindrical shape. Once the boule is formed, it's sliced into thin wafers. These wafers are incredibly uniform, with each one just a fraction of a millimeter thick. After slicing, the wafers are polished to remove any imperfections, making sure the surface is smooth and ready for the next steps. Even though a single wafer is extremely thin, it will soon carry all the tiny, complex circuits that make up a microchip. But what happens next? How do these wafers turn into the powerful chips that run our devices? Stay tuned, because the next steps are where the magic really happens. Now that we have the silicon wafer, it's time to create the detailed circuit patterns that will form the microchip's brain. This step is where things get really interesting. It's called photolithography. Essentially, it's a process that uses light to etch tiny patterns onto the wafer's surface. First, the wafer is coated with a thin layer of photoresist, a light-sensitive material. Then, it's exposed to ultraviolet, UV, light through a mask that has the microchip's circuit design on it. The UV light causes the photoresist to harden where it's exposed, while the unexposed areas remain soft and pliable. Next, the wafer goes through a chemical bath that washes away the soft, unexposed photoresist, leaving behind a pattern of hardened material that matches the circuit design. This pattern is crucial because it tells the factory where to add or remove materials in the next steps. Photolithography isn't just done once, it's repeated multiple times during the manufacturing process. Each time, a new mask and material is used to build up different layers of the circuit. The best part? The patterns are so tiny that the transistors and wiring lines are just a few nanometers wide. But how does this turn into a fully functional microchip? The next step is a hidden secret that will be revealed. Just keep watching. Now that the basic pattern is on the wafer, it's time to give the microchip its electrical properties. This is where doping comes in. Doping is a process where tiny amounts of other elements, like phosphorus, boron, or arsenic, are introduced into the silicon wafer. These elements change the way the silicon conducts electricity, creating areas that either conduct better or worse. The areas that conduct electricity better are called N-type regions, while those that conduct less are known as P-type regions. The interaction between these N-type and P-type regions is what forms the transistors, the switches that control the flow of electrical signals. These transistors are the heart of the microchip, allowing it to process information and perform tasks. To make this happen, the wafer is exposed to gases that contain these dopants. Then, it's heated in a furnace, causing the dopants to diffuse into the silicon. This permanently alters the silicon's electrical properties. The balance between these regions is crucial for the chip to work correctly. Now that the electrical properties are in place, we're getting closer to a fully functioning microchip. But there's still more to be done. How do you think this will turn to the powerhouse that powers your devices? It's a secret, but you will discover in the next step. Stay connected. With the basic layout and electrical properties set, it's time to cut the circuit into the wafer. This is where etching comes in. Etching uses chemicals to remove parts of the silicon wafer that aren't protected by the hardened photoresist. This creates the tiny channels and connections through which electrical signals will flow. Think of it as carving out the pathways for the brain of the microchip. Etching can be done in different ways. In wet etching, chemicals are used to dissolve unwanted material, while in dry etching, gases are used in a vacuum chamber to etch away material. Both methods need to be done with extreme care because even the tiniest mistake could ruin the microchip and stop it from working. After the etching process, the wafer is transformed. It now has a network of fine lines and patterns, tiny channels and connections, that will eventually form the complex circuits of the microchip. These channels are what allow the chip to process information, communicate with other devices, and perform tasks. But it's not done yet. What happens after the wafer has these intricate pathways etched in? How does this turn into the fully functional microchip that powers our devices? We really need to talk about that. This will take us to the next process. Now that the basic layout is in place, the process of layering begins. This step is repeated multiple times as more components are added to the microchip. New layers of materials are deposited on the wafer, and each layer is patterned and etched to form different parts of the chip. It's like building a multi-layered structure, where each layer plays a crucial role in the chip's functionality. One of the most important additions is insulating layers, which help to separate different parts of the chip. Then come the interconnections, which link everything together. In some cases, materials like copper or aluminum are used to create these connections. These metals help form the electrical links between the transistors and other components, allowing them to communicate with each other. These interconnects are what make the microchip work as a whole. Without them, the different parts of the chip wouldn't be able to send signals back and forth, and the chip wouldn't function. These layers are what turn the wafer from a flat piece of silicon into a complex, multifunctional microchip that can power everything from your phone to your car. But we're not quite finished yet. We need to know what happens after all these layers are added. How it turns into the fully functional microchip that makes everything run smoothly. Keep watching because we are going into a new dimension in this manufacturing process. Once the microchip is fully assembled, it's time for one of the most critical steps: testing. Every chip undergoes a thorough inspection to ensure it meets the performance standards needed for real-world use. These tests check everything: how much power the chip uses, how fast it processes data, and if it functions properly in all conditions. The goal is to make sure the chip will perform reliably once it's in your device. To make sure it can handle extreme situations, chips are also tested under high temperatures, mimicking the kind of stress they might face in actual use. This ensures that the chip won't break down when it's put to the test. Automated machines play a huge role in the testing process. They use lasers and other tools to inspect the chips on a microscopic level, looking for any tiny defects that could cause problems. If a chip fails any of the tests, it's discarded or recycled, making sure that only the best quality chips make it to the final product. But what happens when the chips pass all these tests? What is their next fate of life? Stay connected, because we're getting closer to the final step of the process. Once the chips pass all the tests, the wafer is cut into individual microchips. These chips are tiny but crucial. They're the heart of the technology we use every day. After cutting, each chip is packaged into a protective casing. This casing shields the delicate circuitry inside and also plays an important role in connecting the chip to the larger system it will power, whether that's in a smartphone, computer, or car. After packaging, the microchip is mounted onto a board, getting ready to be integrated into a device. Depending on what the chip is going to be used for, it may be sealed inside a ceramic package for extra durability, or it might be placed in a plastic package with tiny metal pins. These pins are used to connect the chip to the motherboard, allowing it to communicate with other parts of the device. This is where the chip begins to take on its final form, becoming a key part of the device you rely on every day. From raw silicon to a fully functional microchip, we've just walked through one of the most intricate and fascinating manufacturing processes in the world. These tiny, powerful devices are behind everything from the computers we use to the healthcare innovations saving lives, and they continue to evolve faster than we can imagine. Next time you pick up your phone, boot up your laptop, or even drive your car, remember that inside those devices are microchips, products of a detailed and extraordinary process that make modern life as we know it possible. Before we go, we need you to do one thing. Kindly subscribe to this channel and turn on notifications so you won't miss out on our next videos. Also, like and share this video so others can see and learn. Now, it's your turn. What new thing have you learned from this video? What is that one thing you want others to know that isn't in the video? Drop your comments. Let's hear from you. Thanks for joining us today on this amazing factory process tour. Until next time, stay curious, keep learning, and never stop discovering how the world around you works.